Hello, everyone. It is really a great honor to have this opportunity for the presentation. Now, I will introduce myself briefly. My name is Ding Yi, and my major is computer science, and my supervisor is Professor Pei. Okay, the title of my research is Exploring the Potential of Discrete Chaotic Evolution Algorithm for Combinatorial Optimization. I have divided my presentation into four main sections. 1. Background. 2. Proposal and method. 3. Experiment evolution. 4. Conclusions. Uh, the term chaos was first proposed by Chinese-American mathematician Li Tianyan and American mathematician James York in 1975. York published an article Pride 3 implies chaos in Mathematicus Monthly and gave a mathematical definition of chaos, which is now called the York definition. Since then, chaos has been given a scientific concept and has become a scientific term. In Li Tianyan's article, the following equation is used as an example to discuss the output of the system when mu take different values. As shown in figure, the x-axis represents the value of mu, the y-axis represents the output of evolution when n tends to infinity. When mu is set to a value from 0 to 1, the point of the system is 0. When n tends to infinity, the system output tends to 0. When n set a value from 1 to 3, x equals to or x equals 1 minus the negative power of mu is the point of the system. When tends to infinity, the system output tends to 1 minus the negative power of mu. When mu is set to a value from 3 to 4. As the value of mu becomes larger, the point of system begins to bifurcate. When n tends to infinity, the output of system tends to the point. When mu is equal to 4, there are infinite points and the system enters a chaotic state. The chaotic evolution algorithm is population-based optimization algorithm. When chaotic evolution algorithm is used to solve the problem of the continuous domain, and the algorithm used the algorithm of chaos to realize the search in whole space. Chaotic evolution algorithm introduce a mathematical mechanism in an iterative evolution process and simulates the traversal motion in the search space with simple principles. Generalizing chaotic evolution of a chaotic vector is a key operation of chaotic evolution algorithms. The target vector is used to generate a mutant vector to simulate the chaotic motion in the simulation search space. By crossing the target vector and the mutant vector, a chaotic vector is generated. In equation 1, di is a director factor and di can take a value of positive 1 or negative 1. CPI is a chaotic parameter. In the interval value is set to a random number in 0 to 1 and it is updated with the iteration of the chaotic system. And propose a new control parameter, director factor ratio dr, used to control the percentage of positive and negative in di to guide the chaotic evolution algorithm search direction. For example, dr equals 0.7. It means that 70% of di is positive one and 30% is negative one. Suppose that an array on left side of figure means individuals, contour lines, and at the right side are the fitness landscape, and the circles on the landscape are individuals. The vector is searched in the whole space through mutation and crossover under the control of parameters. Since the chaotic evolution algorithm has achieved good results when solving continuous problems, we try to introduce the idea of chaos into the solution of TSP problem. We chose taboo search algorithm and simulated annealing algorithm as the comparison algorithm. On the left are the iterative steps of the taboo search algorithm, and on the right are the iterative steps of the simulated annealing algorithm. We also chose the RKH algorithm and Concord as the reference algorithm. The solution time process of the RPA 85900 problem is shown in the figure. As the optimal solution obtained is shown in the picture on the right. The traveling salesman problem is a well-known discrete problem. A representative combinatorial optimization problem is graph theory. The solution to many practical problems can be transformed into a solution of the TSP problem. For example, the operating of the train, the route of the deliver the express, and therefore the solution to TSP problem has always has been high valued. The TSP problem is a classical combinatorial optimization problem. The classical TSP can be described as a salesman who wants to go to N cities to sell merchandise. The salesman starts from one city and needs to pass through all the cities before returning to the place of departure. How should the travel route be choice to take the total travel or the shortest? As shown in figure, the points in the three graphs are the city positions in the TSP problem for 100 cities, 128 cities, and 764 cities. The principle of the chaotic evolution algorithm is to simulate the traversal motion of chaos to realize global search and generate the mutation vector through the process of the previous generation of vector, as shown in figure. The position of mutations are generated by chaotic sequence. For example, two positions, 2 and 7, are selected. Exchange the city number corresponding the position of the sequence A to obtain the mutation vector. The crossover process is shown in figure. Involves determining the crossover positions using chaotic sequence. For example, select the third and the seventh positions. First, I had to select cities corresponding to the select positions of A and B to the front of the sequence of B and A respectively. Second, delay the city numbers that appeared of the second time into sequence. Finally, we obtained the crossed vectors. As mentioned above, we propose a chaotic evolution algorithm, and the following description outlines the main steps of the implementation of the chaotic evolution algorithm. Step 1, initialization. Step 2, generate the internal solution. Step 3, fitness calculation. Step 4, crossover operation. 5, mutation operation. 6, judgment operation. The three pictures from left to right are the city connection maps obtained when the taboo search algorithm processes the three TSP problem. It can be seen from the figure that the taboo search algorithm fails to convert to the global optimal solution in a limited iteration process. It can be seen from the figure that the results obtained by the simulated annealing algorithm are similar to the taboo search algorithm. and it fails to convert to the global optimal solution in a limited iterative process. It can be seen from the figure that the chaotic evolution algorithm successfully convert to the vicinity of global optimal solution in a limited iterative process. The results obtained when the three algorithms deal with the TSP problem with number of cities of 100, 128, and 734. The broken line in the figure represents the change process of the current optimal solution as the number of iterations increase during the operation of the algorithm. From the above three broken line graphs, we can all get same conclusion. The result of the chaotic evolution algorithm is better than the other two comparison algorithms. After running each algorithm 30 times, we compare the chaotic evolution algorithm and simulated annealing algorithm and taboo search algorithm. Through the significance test, the p-value obtained by the comparison between the chaotic evolution algorithm and the other two algorithms is less than 0.05. When the significance level is alpha equal 0.05, the operation results of the chaotic evolution algorithm are significantly different from those of the simulated annealing algorithm and taboo search algorithm. For the TSP problem with number of city of 100 and 128, the LKH algorithm and Concord obtained the optimal solution for each ray, and the distance of optimal solution were 45911 and 17511 respectively. For the TSP problem with number of city of 734, the LKH algorithm was run 30 times, and the global optimal solution was obtained 21 times. The distance of optimal solution is 79,114, and the average distance obtained by the LKH algorithm is 79,116. Concord obtains the optimal solution with the distance of 79144 for each time. First, we tested the performance of the chaotic evolution algorithm using a public available dataset. Second, the chaotic evolution algorithm achieves good results in dealing with problem. Third, the comparison of the results shows that the results given by chaotic evolution algorithm are significantly better than the simulated annealing algorithm and the taboo search algorithm. Finally, in the comparison of the results with the LKH algorithm and the Concord, there is still a gap between the results of the chaotic evolution algorithm and the best algorithm in the world. The performance of the chaotic evolution algorithm was room for further improvement. Therefore, we will carry out future work through the following 2 points. First, choose another chaotic sequence. The chaotic sequence generated by logistic map has the characteristic of uneven ergodicity. We will consider this shortcoming and further improve the performance of chaotic evolution algorithm in the future. Second, applying the idea of chaos to LKH algorithm. We will try to add the idea of chaos to LKH algorithm and propose LKH algorithm based on chaos. That's all. Thanks for listening to my presentation.